nucleus with beams of electrons from the superconducting accelerator. CEBAF has an educational mission as well. The CEBAF Science Series features scientists and engineers who are gifted at making their work not only informative but fun. The Science Series is held once a month during the school year in the CEBAF Center Auditorium. The presentation is live, spontaneous, and for the most part unrehearsed.
Good evening. I'm Beverly Hartline from CEBAF, and it's my pleasure to introduce tonight's Science Series speaker, who's also from CEBAF, Dr. Chip Watson. Dr. Watson was raised in New Orleans, Louisiana, and he had one brother and three sisters, and it happens that they've all grown up to become involved with computers in one way or another in their career. But then I think as time goes on, virtually all of us are going to be involved with computers in our careers. Chip got interested in physics when he was young because he thought it was a lot of fun. So he majored in physics at Georgia Tech, getting a bachelor's degree, and went on to Duke University to get a PhD in nuclear physics. After that, being an experimentalist, he went to Brookhaven National Lab to do an experiment and got involved with the data acquisition side of it. That means what you do, how you get the numbers, how you handle them with computers. And from that point, his career was hijacked and he became a specialist in computers and data acquisition. He came to CEBAF in 1988 to attack the challenge of developing a data acquisition system before CEBAF was taking data that could handle 1 trillion bytes of data a day. However, 2 years ago, we gave him a different challenge, which he accepted, which was to develop the control system to control the computer, which has 100,000 different gadgets which have to be sending information back and forth in order for the accelerator to run. He's told me just before the show that he's the first person on the peninsula to have installed at his own home a high-speed digital network. And he, as you're going to see from the program tonight, he can make computers do a lot of neat things. Dr. Watson has 3 young children, and his wife is a professional violinist. He's going to tell us about basically how you control computers to make them do whatever you want. Please join me in welcoming Dr. Watson.
Thank you, and good evening. I have a lot of interesting things to tell you about computers and computing this evening. We have half a dozen different computers standing by ready to take part in our demonstrations. And there are in fact hundreds of computers here on site at CEBAF that I could ask a question of and get some useful data from. And we'll be doing some of that later in the presentation. You've heard a little bit about me from Beverly, and now I'd like to maybe learn a little bit more about you. How many people in this room have a computer in their home? My goodness, that looks like almost everybody. How many people have 3 or more computers in your home? My goodness, what a bunch of... How many people have 100 or more computers in their home? Okay, we've established that a few people probably aren't telling the truth, and the rest of you, if you want to play with 100 computers, have to use somebody else's. And one of the things I'll be talking about this evening is how to get other people's computers to do useful things for you. Okay. Well, how do we talk to computers? You can try talking to them and say all kinds of things to them, but that probably won't be very helpful. Instead, what you usually do is type on a keyboard. And so I'm going to go over here to my keyboard, and we're going to take the room lights down a little bit so that you'll be able to see what I'm doing. First, I got to get it so I can see what I'm doing. Let's see, we'll get rid of my bouncing ball here and try to find the correct window. That's not it. That's not it. That's not it. There we go. That's the one I want. And let me get a little thing going here. Okay. Now, when I type on the keyboard, that sends a signal over this little coiled wire here into the computer. And deep inside of that computer is a little tiny chip, probably bigger than this one. This is an especially small one. And on this chip, and I'm going to pass two of these around the room so you can take a look at it, you can see little tiny gold wires. And normally the wires might stick out of the chip. In this case, they're just etched on the surface. And I put that down on something that's going to touch all those wires. Okay, so let's pass that around. And I'll start one over here, and you can just pass that one up and around the room till everybody's seen it. Now this computer chip, it's called a CPU, a central processing unit. And it has these wires into which you can send zeros or ones. That's it. The computer only knows 0 and 1. It's, well, that's all we can give it. There are a number of wires on that thing, so we can give it a lot of zeros and ones at the same time and use that pattern of 0 and 1s to represent information to the chip. So, for example, if I wanted to represent the character A, and let's get rid of some of this noise here, it would look like 0, 1, 0, 0, 0, 0, 0, 1. Okay, that's what the letter A looks like to the computer, right there. Okay? And we can get other things displayed here. Let's see, let's take a guinea pig here. What's your name?
David.
David, okay. Want to see your name in lights? That's what David looks like to the computer. Okay, nice interesting pattern there. Nice diagonal line. Boy, I couldn't have done that if I tried. Okay, somebody else. You. Misty, okay. That's what your name looks like to the computer. So all the computer knows is zeros and ones, and we can get a whole alphabet in code to the computer, and it looks like that. Okay? Now, what is the computer going to do with these numbers, these zeros and ones? Well, the computer has a fairly simple set of things it can do to these ones. It can add them, it can multiply them, it can compare them, it can check if a particular bit is turned on or off. And out of all of those things, we get what we call the instruction set of the computer. And the computer knows how to do something on the order of 100 things if you added them all up together. And that's pretty much true of all different kinds of CPUs. They know about 100 things. So the language that that chip that's going around the room speaks is only 100 words. Do you know how many words you know? How many words does an average person know in the English language? Anybody hazard a guess? Holler out. It's about 60,000. If you're a real literate person, you might know 80 or 90,000. You might find over 100,000 words in a dictionary. Okay? So a computer is very stupid. It only knows 100 words. And you probably know, well, tens of thousands anyway. So you're a lot smarter than the computer is. The difference between you and the computer is that it can do things very fast, maybe 100 million times a second. But it's very fast. So it can make 100 million mistakes a second, or perhaps just do something useful for you. Okay, now, one last thing here. I could talk to the computer in its language, something like this, and tell it to add two numbers together. Add is something it knows how to do. But it doesn't know ADD. It knows its own code for the instruction that means to add two numbers together. So the first thing I need to do if I'm going to control a computer is have something that will translate what I type on the keyboard into the zeros and ones that that computer chip is going to understand. And that's an assembler. Okay, that's the most primitive thing. But that would be pretty tedious for me to make a computer do everything I wanted by speaking at that low level. So we usually work with a higher level language. We might have it do some algebra for us, a equals 12, b equals 13, c equals a times b, which I hate that stuff. And then finally print out the answer. Anybody know what the answer is? How good's your math? All right, that's an exercise for your homework. Now, there are many different computer languages, and by this we mean something that I will write some instructions in one language, then a program's going to take that and translate it into the zeros and ones that the computer knows. And the languages that are used heavily here at CEBAF, there's a language called C, which is what most of the control system is written in. And there's a language called Fortran, which stands for Formula Translation, which most of the scientific programs are written in. What other programs do you know? Anybody know another program language?
Pascal.
Okay, we got BASIC here. Pascal. Yeah?
DOS.
DOS? Okay, that's a special kind of language, and I'm going to come back to that in a second. Yeah?
Unix.
Unix is an operating system, not a language, but the shell that we use to talk to Unix with, the C shell, is another special language.
COBOL.
Pardon?
COBOL.
COBOL, a good business language. Others?
C++.
C++. All right, got a smart kid in the crowd there. There are many computer languages: Pascal, Algol, Objective-C, Eiffel. There's some special languages used for simulating hardware, Verilog, VHDL. Dozens and dozens of computer languages. And for each one of those, there's a special program called a compiler that'll turn it into something that the computer can understand. Okay, so that gets us on the road to getting the computer doing something useful for us. Yeah, okay. Now, one person mentioned DOS as a language. DOS, the program that you talk to when you're logged into your PC, is something that will take instructions from you, but it's not a compiler. It's another kind of program called a shell program. And a shell program is just a program that starts other programs. Okay, so in this window right here, I'll get rid of this program. And now I'm talking to a program that every time I hit a carriage return, it just prints the name of the computer I'm talking to right now, which is a computer off in another building on site here. And with this computer, I can enter a command like cd. This is a very cryptic language, change directory. And I'm going to give it a particular path. Wrong path. Okay, so I'm changing to a directory. Then I can type ls, which is short for list, and I can see a bunch of other names. These are names of other programs. So in talking to this shell program, I can get it to start another program up for me, such as, let's see. Uh-oh. Oh, don't worry about it. Not a problem. Or, oh, something seems to be wrong here. Okay, these are just silly little programs. Let's see. What else? Oh, let's get one more going here, and we'll leave it running. Where are the eyeballs? There are supposed to be eyeballs. Ah, I ran out of colors again. All right, never mind. Not enough colors to display the eyeballs. Okay, so a shell program is just a program that will take what you type and go find the right program for you. Okay, so already we're starting to involve multiple programs to do something that we want to do. I have the shell program starting up another program for me. And we're going to be doing a lot of that kind of thing in our demonstrations tonight. Okay, let's see. I already told you how dumb computers are. There's a command called echo, and it just types out, let's get rid of that, whatever I tell it to type out. It's not very smart. Doesn't have feelings either, so I don't have to worry about it. Okay, so I can type things into the computer. I have a program that translates that into doing something useful for me, because the computer, again, doesn't understand characters. I need a piece of software to get it to do something with that. And then it goes and does what I want. All right, so that's one way to talk to a computer, is by typing. How else do you get a computer to do what you want? A mouse. Okay, and actually I've been using a mouse already to point at the program that I want to use. And I use the keyboard and the mouse to give instructions to the computer. And how does the computer respond to me? Generally something on the screen. Now you can also get a computer to talk to you. Unfortunately, the one I have in the room here is not equipped for sound, but others are. Okay, so I have a little demonstration here of ways that the computer conveys information back to me. Okay, what do we have on the screen here? Okay, and can you see the mouse? Yeah, you can see that. Suppose I point at this little rectangular thing here and click on the mouse. What'll happen? Good. Okay, so by using pictures, we can make things easy to use. It was sort of obvious that if I just pointed at that and clicked on it, that the light would turn on. Okay, it's an intuitive interface. Other things that are intuitive are just representations of things that you are accustomed to seeing in your everyday life. A speedometer meter. Okay, all this is a line moving around on the screen, but you associate that with something that you've seen somewhere else, and so you immediately recognize what it is. And so we have all different ways of graphically presenting data. Meters, strip charts, let's see, color, right? Green means, orange means, who said go faster? Are the teachers here? Watch that kid. Okay, what does this mean? What's that mean? Okay, everything's good, no, everything's not good. All right, so we can use all kinds of different things to have the computer display information for us. And we can throw all kinds of symbols on there. And we're going to see later this evening some screens that are actually attached to the control system for the accelerator. And they're over there in the accelerator control room right now, tuning up this machine. And this machine is still in the process of being commissioned. It's being run for the first time. And we are slowly tuning up the energy of this machine, hopefully to reach full energy in another month or so. And so we'll go sort of look over their shoulders in about a half an hour at what's going on in the control room over there. Okay, let's get rid of this program. Okay. Yeah, I guess that's enough of that. All right, so now we've got one computer doing things useful for us. It's making pretty pictures, it's listening to what I type on the keyboard, where I point with the mouse, and I have a computer doing useful work for me. Now, how do I get a lot of computers to do something useful for me? Well, I could surround myself with keyboards. Networking, right. So that's our next topic here, is networking. And what we do is we take more than one computer and we hook them together with a network. And these networks come in various flavors and speeds. If you have a Macintosh and you hook a couple of them together, they can talk, the two computers can talk to each other at 200 kilobaud, kilobaud, right. What's a baud? a bit per second. It's one of those zeros or ones. That means a 230 kilobaud network can transmit 230,000 zeros or ones per second. Most of the networks here at CEBAF are Ethernet. So that's 10 million bits per second. By the way, the network that was into my home goes from here to CEBAF through the phone system, and it's 128,000 bits per second, 128 kilobaud, and that's a digital network. Who knows how fast your modems run that you probably have on your PCs at home? 14.4. That means 14,400 bits per second, okay? Other popular networks are Token Ring at either 4 or 16 megabits a second. FDDI is 100 megabits per second, and we have a little bit of FDDI on site hooking together some of our faster computers. Where we're going in the future at CEBAF is ATM, asynchronous transfer mode, and this is another type of network that can either run locally between a couple of computers or across the country. And the phone companies will be able to provide services on this kind of a network. A very futuristic network is SCI, Scalable Coherent Interconnect, and that will run up to a gigabit per second, 1,000 megabits per second. So this is not quite 1,000,000 times faster than what you have on your PC at home. Okay, and remember we said computers are stupid but fast, so they can talk back and forth to one another very fast, but just sending zeros or ones. All right. Interesting statistic. You probably have a hard disk on your computer at home, at least especially those you people with 3 or more computers at home. Maybe something like a few hundred megabytes. That SCI link could fill that disk, if the disk could eat it that fast, in about 3 seconds. Okay, so that's fast networks. Now, if I take a lot of computers and put them on a network together, how do the 2 computers talk to each other? How do they know which computer they're talking to? Okay, all the computers on the network have an address, kind of like a phone number. And for the kind of networks that are most widely used, the internet, this address is 32 bits, zeros or ones, long, 32 bits long, which would be enough for about 4 billion computers. However, the way the addresses are arranged, you can't quite get that many computers. Anybody know how many computers there are on the internet right now? Everybody that thinks that it's at least 1,000, raise your hand. Everybody thinks it's at least 1,000,000, raise your hand. Everybody that thinks it's at least 1 billion, raise your hand. Wrong. 3 million computers. Okay, there's actually 3 million computers out there right now, and I could probably talk to most of them if I knew their address. Okay, if you know the address, it's just like knowing somebody's phone number. You could talk to them. Okay. Let's see. Now, a lot of these computers, not only do we have lots of computers on one network, but any one computer might be running many programs. In fact, most of the computers are running a lot of programs. So I still need to know, even if I know like the phone number of the computer, I got to know who to talk to inside that computer, which program I want to talk to. So we have another number for that, and it's called the port number. Okay. Oh, an apartment complex or something. The street address gets me to the right building, but I need to know the apartment number to get to the right person. Or maybe you need to go out in the hall and call your friend. You know the phone number, but still, when somebody answers on the other end of the line, you say, "May I speak to so-and-so?" If you're polite. Otherwise, you say, "Gimme so-and-so." Now, the computer network's the same way. That there are a lot of programs running, and some of them are listening for other programs to talk to them, and they're listening on a particular port number. Let's make this screen a little bigger for a second here. This is a list of all of the programs that are listening on this computer for somebody to talk to them. As you can see, there's a large number of them. All of these are programs that are willing to do your bidding if you talk to them. Let's pick one useful little program. It's a program called Ping. Let's see. Let me just make myself a little shorthand here. I think is correct. Okay. So I just started up a program that will ping another computer on site. So I had one computer here. I'm typing into a computer called DevServe, and I pinged a computer called CEBAF-A, and that just means I sent a message to it, and there's a program on that computer that just caught the message, turned it around, and sent it back again. That tells me two things. Is the computer up? It is, because it answered me. It also tells me something else. It tells me how far away that computer is, sort of, by how long it took the reply to come back. So ping is useful to find out if a computer is up. All Unix computers and pretty much all computers will respond to ping messages. All right, let's pick a different computer here. This is a computer in Japan. Now, if you look at this display here, you can see, except for the first time, when I sort of had to wake the ping program up, it was asleep. It responded each time after that in 2 or 3 milliseconds. That's thousandths of a second. Very fast, fast as a blink of an eye. Now I'm going to talk to a computer in Japan. And you can see each time it replies, it's taking a couple of 100 milliseconds. But that still means I'm sending a message from here to Japan and getting it to come back in less than half a second. Okay, you can't call somebody on your telephone that fast. So that's how fast these computer networks are. Let's pick one more. Let's see, Australia or England? Australia. Oh, I typed something wrong here? Well, you got to know the computer's name. Now, notice that I haven't been typing in numbers. There's another set of programs running on the network that'll translate names into numbers for me so I don't have to remember phone numbers. It's as if you could type into your telephone the name of the person you're trying to call, and it would know the phone number for you. So we have that with computers. All computers have a unique name. All right, we'll have to go with England then. And England seems to be a little slow today. Had one of them that was actually longer than a second. Networks must be clogged up. Oh, and that's this list at the end, by the way. This is a list of all of the computers that my message went through on the way to England and back. Because my computer is not connected to the computer in England. And so that's another set of programs that are always running on these computers. It's just a program that will take the message, look at it and say, oh, that goes that way. Get the next message, oh, that goes that way. And they're routing these messages. And the message just sort of travels through this net of computers until it finally gets to the correct destination. And you can see it took 8 or 10 computers to forward my message there and then get it to come all the way back. And all of that in less than half a second. Okay, computers are fast, although dumb. All right, now all these little programs that we're using on other people's computers, like this, are called daemons in the Unix jargon. Daemons because they inhabit the computer, I suppose. And there are a lot of useful daemons that we will use to get work done on the computer network. Ping is just the simplest of these daemons, the ping daemon. There are other programs that let me talk to another computer from the one I'm logged into. So I'm logged into this computer. I can ask it to log me into another computer. Let's say we'll go to CEBAF A. And now CEBAF A is asking me for my password. So you can't use a computer unless you know a password sometimes. Okay, now I'm talking to CEBAF A. And the reason I can do this is because there's a daemon running on CEBAF A that's listening for anybody to attempt to make a connection to it. Okay, and there are lots of these daemons in these computers, in the networks, for phone, for file transfer, for a lot of other interesting services. Now, if you've been reading almost anything, you've been hearing a lot in the past year about the internet. Okay, the internet is just this bunch of computers that are all connected together by a network called the internet. And the internet is a very interesting thing. Nobody owns the internet. It's just a bunch of computers that are cooperating with each other. If you want to get onto the internet, you just need to hook your computer to another computer that's on the internet who is willing to route your messages for you so that you get into the network that way. And there now, in the last year, have sprung up a large number of commercial internet access providers that will sell you a connection into the internet. Being on the internet is not free. CEBAF spends tens of thousands of dollars a year to maintain its connections to the network. The reason we spend so much is because our network needs to be very fast. In your home, you don't need that expensive a network. So the network, the internet, is this 3 million computers owned by thousands and thousands of different people with no organizational ties to each other. It spans the entire globe. As you've just seen, we've gone to England and Japan. Earlier today, I got to Australia, but I don't know the name right now. So that's what the internet is. Now, an interesting thing that's been going on the internet in the last year is another kind of service or set of daemons or servers, they're also called the World Wide Web. How many people have heard of the World Wide Web? Okay? And all this is another one of those programs that's just sitting there listening on a particular port number for you to make a connection to it. And the web, shorthand for World Wide Web, is sort of like a set of encyclopedias. Okay, you go to the encyclopedia and you pull one encyclopedia out and you read the article that you looked up, and at the bottom it says, see also something else. For example, if you were to go look up catacomb, all right? You would come to the end of that article and it would say, see also crypt, labyrinth, something else. You look up crypt, you read that at the end, it says, see also tomb. Okay, well, when I went from catacomb to crypt, I was still in the same volume, so I didn't have to do anything. But when I went to tomb, I had to put that book back, go to T, and pull that one out and open it up. Okay, well, the web is sort of like that set of encyclopedias where each book represents one computer. So I will be reading a page of information on one computer, and there'll be like a see also, and maybe it points to something on the same computer, like from catacomb to crypt, or maybe it points to something on another computer. And when it points to another computer, it's giving me the name of that computer, the port number on which the server is listening for me to talk to it, and some piece of information to reference what page it is that I want to look up tomb. Okay, so that's how the web operates. So now I'm going to start up, let's see. I'm going to start up what's called a web browser. Basically, it's just something that will read this big book. Looks different. Wrong computer. I don't want to run it on this computer. Let's try this one. That's the one I want. I want to run it on this computer because I've I have some information cached here that'll make navigating around a little faster. Okay, so here's the opening page for this book for us, and it has some information here about CEBAF. Now what I'm going to do is I'm going to use my mouse, and I'm going to point at one of these underlined phrases, and that's like a see also. So let's pick something here. General information. Okay, how about news? All right, how about second announcement? This is an advertisement, by the way. So what I'm doing is I'm walking through this book just by pointing at things. All right, now let's just go backwards here. Where else could we go? Computer Center. Let's see. Computer Center staff. Picture of Computer Center staff. Okay? And you can just wander around, looking around through this book. This book is quite large. Let's see. I think, here we go. There's 12,000 computers on the network that have a volume in this book. And the number of computers that have these web servers running on them is growing exponentially. Okay, it's growing very fast. Okay, there's a picture of how fast it's growing. So in April of last year, that's this point right here. Yeah, point there. Oh, you can't read this very well, can you? All right, follow the pointer. In April of last year, we had a little over 1,000 servers running. Now we're nearly up to 12,000 servers. It's gone up a factor of 10 in less than 1 year. So it probably will continue to go up another factor of 10 in the next year, and maybe even another factor of 10 the year after that. So we're going to have a very large set of encyclopedias. It's huge. You could spend years wandering around through this book. And I thought I would take you on a little guided tour of some things inside this book. I have some bookmarks here that I've saved here. Let's see. University of Purdue maintains some weather information for us. Maybe you want to know what the weather looks like, and your cable television connection is down. Or you're in your office at work and you don't have TV in your room. Although we'll get back to that in a minute. So here's a weather map. It looks like it's raining in Mississippi, and still clear here. Looks like we probably got another good half a day of clear weather. This gets updated about once an hour. So if I were to come back and bring this picture up again an hour from now, the picture would be different. Okay, so this is not a static book like a set of encyclopedias is. When you get your set of encyclopedias, all the information in it is already a year old by the time you get it. The information right here is about an hour old. Okay, so this is great for accessing information that could be rapidly changing. Now the problem with this great big book that we have is there's no table of contents. Okay? The web is running on computers all over the world. They don't belong to one company. There's no place where we could make a table of contents. But there are some useful programs that are, in effect, going around reading the whole web. A program doing this. And it, let's see. It's accumulating this information on its own disk, and it's saving it up and making it available to me. So this is a server. Now I got to find the right page to get into the server here. List of robots. Let's take that one. These little programs that are going around reading this set of encyclopedias are either called worms. They're crawling around through the web. Robots, spiders, all kinds of different things. Now let's see. These things tend to get a little busy in the evening, so I may try a couple of different ones before we get one that responds to us fast enough. We'll try the World Wide Web worm. Let's see, where's... that's no good. Let's go back up here. Jump station. Okay. Now, I just brought a page up in this document, and not only can pages be updated every time I ask for them, but this is a very strange book. I can talk back to it. So I'm on a page in the book where I can type something in. And I don't know what kind of luck we'll have on this search, but let's try shuttle. Whoop. No guarantees. Okay, so it's searching right now for any page of the book that has shuttle in the title. And pizza shuttle, oh my, that's probably not what I wanted. Pizza delivery service, and probably not in the peninsula. Space shuttle is really what I wanted, so we'll pick that. Okay, it can't make that page. Let's try this one. Okay. So this is about the Space Shuttle Earth observation program. That's what's up in space right now. And let's see if I can find the right page here. There's another set of services running that maintains video pictures that are always running around on the network, and all I've done is sort of tuned in my computer to watch that video. We seem to be running out of colors here. Oh well, false color. This is the live shuttle mission. We're talking to mission control. I don't know what we're looking at right now, probably results coming from the telescope. Earlier this evening, there were live scenes from the shuttle up in orbit. So there's a television picture coming down to the Earth station, and that Earth station, I don't remember which one, is then sending that signal out onto the internet where people can listen to it. If I had sound here, we could even hear what the astronauts are saying. Okay, so the internet is a wonderful communications device. Let's get rid of this because it's messing up my colors. Okay, then I could go and browse around here and look and find more information about the shuttle. And all of this information potentially is right up to date. It's very current. I don't have a bookmark marked on that page, but there's a page that you can find that will tell you exactly where the shuttle is right now. Is it over Africa? Is it over South America? It'll give you right up to the minute information on where the shuttle is. Okay, so this is a pretty marvelous book. Time magazine is online. So if you don't want to pay for your subscription, you can sit here and read Time magazine online. Let's see. What do we want to read about here? The cover story? No, I've had enough of that. Obituaries? No. Okay, I guess there's nothing here I want to read. You can also get to local news. The Virginia Pilot is online. I can get up-to-date information here. Daily news summary. Oh, I just jumped back to Time. It's a funny book. You never know where you're going. Local news, that's what I wanted. Okay, so if I want to read more about this plane crash, I can read that here online. Okay, and all of this works because there are these server programs spread all through the network listening to the messages that I'm sending. But I'm not even having to type anything now. I have a program here that when I click on something, it does everything I need it to do. Okay? All right. Let's do one more thing now. I'm going to shut this down. Find the right computer again. Oh, I guess it doesn't matter. We'll just take a jump over there. Now we'll go spy on what's happening in the control room. for the accelerator. And what I'm doing now is logging into one of the control computers over there. Yes. It didn't know where to send the picture to, so I have to tell it that. Now the computer that I'm talking to right now is very busy trying to run the accelerator, so it will be a little slower than the World Wide Web was. Okay, and as you can see, most of the things that I'm going to do with this program is just point at things. Okay, so this is sort of a main control panel, and I can look at one section of the accelerator. So that's sort of a picture of one little piece of the accelerator, and then from there I could get into things that would let me control magnets and look at vacuum and things like that. Let's see, what do we got here? We'll look at the vacuum system for a second. So there's a picture of the accelerator. The beam starts here. That's the injector. Then it's accelerated along a linac, gaining energy. And then we whip it around, and we send it back through another accelerating section. And then we whip it around again, back through an accelerator, around again. And eventually, the beam will go around 5 times and then be steered to one of these 3 buildings where the experiments will take place. And I think they're still going around the first time right now. Let's see if we can get a look at what they're doing. So I'm bringing up a display of beam position monitors. We'll start with the injector. Okay, they have beam. So each one of these little colored bars right here represents one measuring device in the beam. So the beam is going to go past it, and it's going to sense the fact that the beam went past it and tell me how much beam it saw. And this is the sum right here of how much beam. And this indicates whether the beam was a little bit steered to the left or the right or up or down. So you can see right here at the beginning, it seems to be steered off to the side a little bit. But then for the rest of the way, it's pretty much in the center, and pretty much in the center there. And I can immediately tell that 2 of my beam position monitors are not working. Because obviously, if the beam got over here, and it was over here, it must have gone through this hole. But the monitor didn't see it. Okay, so we have 2 dead BPMs. And it seems like we're getting all the way to the end of the injector. All right? Let's go to the next page then, which is the north linac. That's that first straight section. And it looks like we're getting all the way through that section too. So straight through the north linac, no problem. Go away. All right, first pass through the east arc. Oh, we're doing good. It's all the way around the first arc, and it looks like I have another dead BPM. Now, in all of these things, every one of these numbers that you're seeing on a display like this number right here, and you can see they're moving right now. The beam is wiggling a little bit. Every one of those numbers has a name. In fact, I can even have the computer display the name. You won't be able to read it. So I'll pick this one right here. And here I can see the name of that thing I just picked. So just like the computers have names, and the programs running on the computers have port numbers and often also have names, here in my control system, any signal that I want to look at also has a name. So if I know the name of the signal, then I can ask the computer that's connected to that signal what the value is. Okay? And what we're doing is we're talking to a lot of little computers that look just like this. This is a not exactly state-of-the-art computer, but it's pretty good. This is a 68040 chip processor, and this round circle on top of it here is a heat sink. It generates a lot of heat on that one chip. And this plugs into a crate that other electronics are plugged into, which is how I'm reading all of the data in. So this computer talks to other cards that are plugged into that crate. So when I bring this picture up, what is happening is the program that I'm talking to right here yelled out all of these names. I want to know the value of XYZ. And then all of these little computers said, oh, somebody wants to know the value of XYZ. Do I have that one? Nope, I'll just shut up and not listen. But one of the computers does have the value of XYZ. It says, oh, I've got that one. The answer is 100, and responds back to my computer. So there are, in the control system, 40 of these computers listening for my requests like that and giving me the answers back in the form of these numbers. This is not one computer that's doing all of this. This is 40 of these little computers, and then about 10 conventional computers. So we're involving about 50 computers here. Okay, so we got around the East Arc. Let's go check out the South Linux. Let's see, South Linux. That's shorter than I expected. Okay, they're all the way through the South Linux. It's a good day. Let's check the West Arc. Okay, we finally found the end of the beam. Right here at the end of the West Arc, the beam is disappearing. Okay? And you can see that they're still trying to steer it right now. Okay, so it's wiggling down, wiggling up, and then they lost it right here. So basically the beam ran into the edge of the pipe that they're steering it through. And so then we don't see it in the next sensor. So this display right now is in the control room, and there's operators in there right now looking at this same display and tuning the beam up. And in some cases they're using automatic programs that help steer the beam, and in some cases they're doing it manually. Oh, something crashed. All right, so they just lost the beam in this whole section, and we'd have to go back. They have, in the control room, they have multiple of these displays up, and so that they can see where the beam is in the whole machine. I can only easily look at one piece at a time. And we can go see how bad this crash was by going back to the injector and see if the beam actually shut down all the way. Yep. Not even in the injector do we have beams. So something happened in the machine that the machine decided they had to shut the beam off so that the beam could not hurt the machine. Now, while they're tuning the machine up like this, they're running the beam current very, very low so that it won't hurt the machine very easily. When this machine is running at high power and doing physics experiments, the beam has enough power in it that it would go through a millimeter of steel, you know, that would be like a plate, a little plate of steel, thin plate of steel, in a millisecond. Yeah, that's right. It would go through a meter of steel in 1 second if it could stay straight through that whole meter, which it couldn't, fortunately. So the beam pipe that this thing is going down through is very thin, and if we hit the beam pipe with a high-powered beam, we have to shut the beam off in 10 microseconds. Actually, we get a total of about 20 microseconds, but the decision-making only has only about 10 microseconds to go. Then it takes the rest of the time to actually shut the beam off before the beam would actually punch its way out through the beam pipe. It wouldn't get anywhere because, in fact, this whole thing is buried 30 feet under the ground. But it could hurt something, some expensive things. Okay, well, I'm glad at least they had the beam up for us for a little while. It would have been not as exciting to bring up these displays and see nothing. Got lucky. Oh, all right. There's a lot of other displays that I can look at that sort of tell me about the status of the system. I have a display here that I can bring up that will look at all of the computers in the whole control system. And this first column here will tell me the fact that they're running. They're just sitting there adding 1 to that number, so I should see all of those numbers counting. These white lines are computers that are not in use right now. And it looks like everything is okay there. I can bring up another status screen here. And this is what we do. I can do this from my office. I can do it in the control room. I can also do everything that I've shown you here tonight, I can do from my home. In fact, I can have one of these in my home and do it exactly, or there in my office. The computer networks make it not really matter where you are when you're working on the computers. Now my time is pretty much up. I've got maybe 2 minutes left. So why don't I throw it out for questions, if anybody has any questions that they would like to ask about what you've heard tonight. Yeah?
What about America Online? Can you describe the different computers?
Can you what?
Like something different computers on America Online?
Yeah. The question had to do with America Online. America Online is an internet provider, and it would let you do the same sort of things I'm doing here. Not as fast as I'm doing them, because your connection would be slower. One more here.
The internet is somehow connected to the information highway, right?
Yeah, the internet is in fact this information superhighway. When they talk about the information superhighway, they're talking about just making the internet bigger and faster. That's what it is. Okay, if anybody else has any questions you'd like to ask, feel free to come on down and I'll stay around for a few minutes and answer your questions. Thank you. Sure.
If you need it signed to get permission to get credit for being here, you're supposed to get people outside to sign it, okay?